Welcome, a new class. The student in the last class, we discussed the second isomorphism theorem. We provide a proof of a second isomorphism theorem, and then we have to discuss three examples using the how to use this second isomorphism theorem and find the element in this form. Though this class we have to discuss the third isomorphism theorem. This is the last theorem of this section, isomorphisms. So we have to in this class try to provide a proof of this third isomorphism theorem, and also try to one or two examples we have to take into use this isomorphism theorems in this lecture. So let's start with the statement of this third isomorphism theorem. Is saying that let G be a group and N is a we have a N is a clearly is a normal subgroup of a G, and H is also is a normal in G, and N is also normal in H. Then he's saying that then you have to just say that this H is N is a normal in H, and H by factor group is a meaning. Clearly we have to just say that. So this means clearly this is a meaning, and then he's saying that is a normal to G by N. G by N is also meaning because G is a group and N is a normal in G. So this is also meaning. So now he's saying that then H by N is normal into this quotient group. This H by N is normal to G by N, and if it's normal to G by N, then we can say that this G by H is again is a quotient group, is a meaningful because H is a normal in G, the quotient group is a defined, and then this normal group is isomorphic to the quotient group of G by N over H by N. So this means again we have to giving in this form. D means giving you have a N is giving normal subgroup of a G, H is giving you a normal subgroup of a G, and N is a normal in H. So first objective is we have to prove that this factor group our factor group H by N is normal in G by N. First we have to show that this is normal into this, and after this we have to try to find a one bijective onto homomorphism, define onto homomorphism from G by H to any of this. Then we can say similarly G to this factor groups. So we can show that or G to G and then we have to find the using the first isomorphism theorem, and then proof is completed. So let's start the proof. We have to first we show that this H by N is a subgroup of a G by N, because we have to show that H by N is a normal subgroup of a G by N. If a normal subgroup means we have to show that first is a subgroup and then is also normality condition. So we take a if this is a subgroup of a G by N, take any two elements of this, because element of this is the types of a Hn types. So H1n and H2n is the element of H by N, and then we have to show that H1n and H2n, and then by the property of coset we can say factor groups, we can say that this is nothing but is equal to you have H1 H2n, and now this is that H1 and H2 are the element of H. So this is the element of H, and N, so this is the element of this is clearly this is the element of Hn. So we have to show that this is also the element of Hn, means is closed. If it is closed, then we have also show that next time is the inverse also exists, or we can combine these two. We can say that so this clearly N is the element of a because identity element the H by N is identity element of this is equal to N. So N is clearly is the element of this. So this means H by N is not equal to empty. So at least identity element in this quotient group. So this means H by N is clearly is not equal to identity. Now since we take two elements NH or NH inverse, now you know that N of H ka inverse is the same as by the property of a quotient group. This is nothing but equal to H n of H inverse. So this can be NH inverse. And now again, by the property we can use is the form NH is equal to NH and inverse by the quotient group property. So NH inverse, and this is the element of a N. Sorry, this is the element of a you have a, sorry, this is the element of a you have a H. So this is NH. So this is nothing but whole thing is element of a H by N, and then we can say that this NH inverse is the element of a N by H. So if it's element of N by H, this means H by N is a subgroup of a G by N. Now our next objective is to show that this H by N is a normal in G by N. If this, now we have to show that this H by N is normal in G by N. So you take any element of this G of N, yeah, N of G, or you have a N of G is the element of a G by N, and then we take a G and we take a N G, so we can take a N of G, and then element of this is equal to, we have a N of H, and then we take a N of G inverse, and this is the element of a, we have to show that this is the element of a H by N. If we have to succeed to proving this, then clearly we say that this is H by N is a normal subgroup of a G by N. So to prove this, we take a N H is the element of a this, and G is the element of a G by N, and find that we have to just say that either take a NG, NGH, NG, and now by this property you can the NG, NH, NG inverse, and now this is nothing but is equal to you just take a, first you had to take into this form, so this can be written as the N of GH, and then we have a NG inverse, and this can be written as NG inverse, and now because you have a this is H is a normal, so this means by the H and H is a normal, this is the element of a H, and this is the element of H, this is nothing but is equal to, this whole thing is the element of a N of H. So this means we can say that because H is a normal in G, because H is a normal in G, so by the normality of a G we using here, and then we have to show that this is the element of H by N. So this means we can say that by this, this inverse is this into this element is also inverse, also belongs to the H by N. So this means we can say that H by N is normal by G by N. So now first objective we have to prove that this is a clearly is a satisfy this condition. So this is a normal subgroup. So this means we have to, these two quotient groups are normal. And now if we have to show that G by N, and we have showed that H by we show that H by N is normal in G by N. Now we define a one onto homomorphism phi of G by N to G by H, because we have to show that show that this isomorphism, this one G by H is G by N into H by N. So G by H up to G by N we have to taking a map from this to this, and we have to just using the first isomorphism to onto homomorphism. If we define into this form, if we show that this phi is onto homomorphism, if phi is onto homomorphism, then we can say that G by H is isomorphic to G by H is isomorphic to G by N over kernel of a phi, and then we show that the kernel of a phi is nothing but equal to H by N. So this means we can say into this form we have to try to proof of this. Let's this we have to define a map this, and then first we show that in the form of a, the element of a this is equal to NG types, and the element of a this is equal to HG types because of the quotient these factor groups quotient are there. So now first we show that this is a map is a well defined, and then if you have NG1 is equal to NG is equal to NG1, and NG, and now you have, you know that HG is equal to H of G1, and then this can be, G can be written in the form of a N of G1, and then by the property of a coset, and this means N is the element of N is the subset of H. So this is N is the element of H. So this is element of H. So this means G is the element of H of G1, and if G is the element of H of G1, then again G is the element of H, then G can be GH is equal to H. If G is the element of H of G1, so that means we can say that H of G is the same as a H of G1 by again the this property of a coset when we say that G is the element of H if and only if we have to show that GH is equal to H. So this G is the element of H of G1, then H of or we can say that reverse is this is also true for a right coset H of G is also is equal to H. So that means we can say that if G is the element of this thing, then H of G is the same as H of G1 by the this. So H of G is equal to H of G1. So we can say that HGG1 is the same as equal to this form. So this satisfies this H of G is equal to this. This means we can say that phi of n of G is the same phi of n of G1. So this means clearly we can say that the phi is well defined. And now we have to show that second thing is this map is a onto homomorphism. So first we try to show that next is this phi is onto phi is clearly phi is from the definition of a phi, and this is clearly Hg is there and G is there. So by the definition it is also clearly we can show that this is a onto. So now we have to show that this phi is homomorphism, and we take two elements ng1 and g2 in the element of this. So we have to take a n g1 and of g2, then this again using the property of a n of g1 g2, and now by the definition you have to just say that you define the h of you have nothing but equal to h of g1 g2, and h is again so the normal, so h of g1 h of g2, and then it is equal to phi of n of g1 and phi of n of g2. So we have to show that clearly these two phi from this group are also is homomorphism. So if it is homomorphism, then the first isomorphism theorem is saying that this onto homomorphism, then G by H is isomorphic to G by N over kernel of a phi. So G by H to G by N we have to define a map. So this means we can say G by N kernel of a phi. Now our objective is show that what is the kernel of a this phi is there. So if we show that kernel of a phi is the H by N, then we have to complete the proof of a this third isomorphism theorem. So let us try. Finally, we have to show that the kernel of phi is equal to H by N. So start with kernel of a phi. Basically, Ng is the element of a G by N, and then phi of G is equal to you have a we have a identity, and identity of this set is equal to H is identity, and then we have to clearly say that into this form, because this map is defined. You have a clearly a G by H, and then identity element of this G by H is equal to you have a H. So clearly we can say identity element of this, but Ng is equal to H of G, and you know that again you have to use the property H of G is equal to G implies and implies G is the element of H. So G is the element of H, and Ng is the element of G by N, and then we can say that this is nothing but is equal to this is G is the element of N, and this is means N is a normal. So this means this is nothing but is equal to this is a complete is nothing but is equal to you have a G by N. So kernel of a phi is nothing but is equal to, we can say that because Ng is the element of G by N, such that G is the element of a H. If G is the element of a H and this N is the element of this means this G by N is nothing but is equal to is the this is nothing but is equal to H by N. So this kernel of a phi is nothing but is equal to this restricted from H. So this means this kernel of a phi is you have a this H by N. So this means we have to show that this so that we can complete the proof by the isomorphism theorem. So we can say that G by H is isomorphic to G by N over kernel of a phi by the first isomorphism theorem, and the kernel of a phi is equal to H of N, and then we have to complete the proof of this third isomorphism theorem. So this completes the third isomorphism theorem. So let's try to we have to next we have to the some examples. Let the similar example for we using the second isomorphism theorem, pz and qz, p and qb are two positive integer, and such that the condition is p divides q. Pz and qz are normal subgroups of z, and then qz is normal to pz, and then by the third isomorphism theorem we can say that z by pz is isomorphic to z by qz over pz by qz. Especially if we take some element p is equal to 4, q is equal to 12, then z by 4z is equal to nothing but is equal to you have 4z, z by 12z is nothing but is equal to z12, and that means z4 is isomorphic to z4 over 4z over 12z and 4z over 12z. This means we can say clearly this if we have generally proof for any p and q are two positives integer where p should divide the q, because we have to show that pz and qz are normal subgroup of z and qz is a normal in pz, then by the third isomorphism theorem we can prove this result is hold into this form. Okay, so now we have to one more example. We take a group of G is equal to group of Z30, and H I take a subgroup generated by this 5, and N is generated by 10, and then clearly you just verify yourself. This H is a normal subgroup of a G, and N is also is a normal subgroup of a normal subgroup in G. So this means clearly this means we have to show that this H and G are normal subgroups of this G. So we take a cosets of a H plus 0. We take a H H plus 0, and then we have a H plus 5 and 10, H0, 5, 10, and so on. So we have to just take a this is equal to, you have a giving the H, and now H plus you have a take a 15, 20 and 25, this giving the this coset, and you have a with 1, 6 and 11 is giving you this coset, because this is a 30 elements you have a Z30 is equal to you have a 0 to 29, and then you have a similarly you have a other element for 16, 21, 26 is giving you this cosets, and then 2, 7 and 12 is giving you this coset. You can verify this, for example H plus 12. If you take a 12, you have a H plus 12. I just verify. So I take this 0 plus 12 is equal to you have a 12, and then 5 plus 12 is equal to you have a 17, and then 10 plus 12 is equal to you have a 22, 15 plus 12 is equal to you have a 27, and then 20 plus 12 is a 32, and then you have a 2, and then you have a 25 or 25 plus 12, 25 plus 12 is equal to 37, 37 is equal to you have a giving is the 7. So this is equal to 0. So this is clearly you have a 2, 7, 12, 17, and then you have a 27. So this is this way we can just say that is equal to clearly this is a coset. Similarly, if you want to take a H plus 26, I just take a one more H plus 26. So you have a 0 plus 26 is equal to 26. Now you have 5 plus 26 is equal to 31 is equal to you have a 1, and then you have a 10 plus 26 is 36, you have a 6, and then you have a 15 plus 26 is equal to you have 41, 41 is equal to 11, and then you have a 46, 46 means you have a 16, and then you have a 25 plus 6 20 51, and 51 is equal to you have a 21. So you have a 1, and you have a 6, 11, 16, 21 and 26. So this is the one coset is there. So we take a because you have a 0 is there, we have take a 1 is there, 2 is there, and now we have a 3 is missing, and then 3 is left, and then all of them is we take a coset into this form. Let's there is another missing term is a 3, and then we have take a 3, 8 and 13 is giving the same coset. Similarly 17, 32, 27 is giving the same coset, and 18, 23, 28 giving the same coset, and also 4 and 14 is also giving to the same set. And finally we have to, this is the our total cosets. So if you see, we have total number of cosets 1, 2, 3, 4, 5 and 6, 7, 8, 9, 10 total cosets for this h which n. And now we have to calculate the another with the g by n cosets of this n plus g. So n is equal to, you have a n is equal to, you have a simple is equal to 0, 10 and 20. So 0, 10, 20 is giving the same thing. Now 1, 11, 21 is giving the same coset. If you want to 21, I take it 21 plus 0, 21, and 21 plus n is equal to 10, you have 10, 21, 21 plus 31, 31 is equal to, you have a 1, and then you have a 20, and then 20 plus 21 is equal to 41, 41 divided by 30 is equal to 11. So you have a 1, 11 and 21 is the simplest. 24, if you want, I just take it 14, 1. So this is 14, 1 is giving the 14, and then 10 plus 14 is equal to, you have a 24, and then you have a 20 plus 14 is a 34, you have a 4, so you're getting the 4, 14 and 24. Similarly for 4, you have a 4, 14 and 24, and similarly for 24 are there. So these are the subgroup we have to calculating into a different values of this. Similarly for other, if you want, you have a clearly 0, 10, 20. So you have a 0, 10, 20. For some other, if you want 25, so 25, 35 is equal to 5, and 45 is equal to, you have a again 15. So this is the same thing. Similarly we have to calculating all these cosets are there for g by n. And now we have a coset by h by n, g by n. Now we have a coset by h by n. And now you can just know that n is equal to 0, 10, and h will be 0, 10, 50, 20, 5, 15 and 25. So we have only h by n as these two cosets are there, h by h 0 into this form. So now we have to, now the cosets of the form of the element of a this plus this and h consists of two coset of the cosets are, so this plus this n plus 0, and this is, we can write h by n. H by n means we have a this can be written as a again is a coset of this thing. So this is the h n plus 0 is this form, and this coset we have to write into this form. And now if we have to adding these two, we getting into this form. So by this we have the 0, 10, 20, and then we have a 5, 25 and 30 to 45 is equal to 15. So this is this coset is into a this form. Similarly 5, this is equal to we have a 0, 5, 10, 20 into this form, and then we have a n plus 5. So this is again into this form. Similarly n plus 1 into this form, and this is equal to, we have to calculating into this form. So we have all the different cosets we have to calculating. Similarly n plus 2, and then we have to h by n we have to calculating in the back side. So this is giving to this form. N plus 7 we have to calculating as substitute value of this, and h by n is equal to this, and then we have to this n by 7 into this, and then clearly this and this we have to 7, all this thing we have to calculating 0, 5, 1, 6, and then 2, 7, 3, 8, and then 4 and 9, and then we have to finally this complete the list of all the these cosets. So now we find a natural isomorphism between g by h, and we have to calculate this coset, because this coset, the natural isomorphism h plus I to n plus I into divides by h by n. H by n I'm just writing the form. This is also the h plus n form. So I running we have a 0, 1, 2, 3, 4. H plus 0, all this, we have 4 cosets are there. So this is maps into this form, and this is map because there is these two coset this, and then we have a, this is mapped into this form, and this coset is equal to, you have a 0, 5, 10, 15, 25. So you just take a 0, 5, 0, 5. We have a, this coset is equal to 0, 5. Where is this? Okay, here 0, 5, 10, 5, 15, 25 is this coset. As clearly this is mapped to this is mapped to this, and this one, second one coset is mapped to this, third one coset is mapped to this, third one this one is mapped to into this way, and then finally we have to into this form is to mapping into this form. So in this way we have to calculating all this thing, apply the third isomorphism theorem, and then we have to show that this is can be written into a this form of the all the this third isomorphism theorem. So now I hope you have to understand the what the meaning of a this three important isomorphism theorem. We have to use first fundamental theorem of homomorphism. In this fundamental theorem homomorphism, if we have to take a homomorphic image, then in place of this if phi is onto homomorphism, then this is a special case of a first isomorphism theorem is nothing but is a special case of a fundamental theorem of a homomorphism, and then we have to prove the second isomorphism theorem, third isomorphism theorem, and each of the theorem we have to provide a very different types of examples, and this is one of the example. Last one is we have to calculate all the different types of coset, and then we have to define how do we have a bijective map can be defined into a one coset to another coset. That is very clearly we can mention into all this thing very simply. We take some groups as there. So now I just conclude with the this remark. For any number of isomorphism from phi zm to zm is nothing but is equal to, you have a is the same as a Euler function of a phi m. Simply you can say that phi of you have a z2 to z2, then phi of you have a, this is a Euler function. This means you have a phi of 2, and then simply you have a, or if you have to take a phi of z 5 to z5, then there is a possibility of a how many isomorphism you can number of isomorphism from this to this is phi of m. This you have a phi of 5, that means is equal to because it's a prime, so this means p minus 1 phi of p value. So there is 4 different isomorphism you can find from the z5 to z5. So I think I have to stop today's lecture by this remark. So that means we have to complete the this portion of a isomorphism today, and in the next class we have to discuss the automorphism, and I already defined the definition of automorphism. You have a, when we have a map from G to G itself, and is isomorphism from G to G itself is called as an automorphism. So in the next class we try to define different types of automorphism. That is one of the inner automorphism. If it is not an inner automorphism, then we can say that it is an outer automorphism. So we have to discuss all these properties of automorphism and try to some other examples in this direction in the next class. So I stop today here. So thank you very much for today's lecture.